Okay, great. So, how many people did the homework? Oh, come on. All right, well, anyway, I'll show you what the homework would have looked like. So what we did yesterday was we finished up in the morning by running two runs of Skyline at 10 ppm plus or minus 5 minutes, and it seemed like a lot of people said that they got to the point where they saw the two runs complete about 15 to 20 minutes each, right? You had a command prompt that told you, okay, I ran 6664 window in 20 minutes or so, and I ran QE plus 19 window at 15 minutes or so, or something like that, right? Everybody, is there anybody who didn't even get that far yesterday? Who was here yesterday? Okay, and then sort of the homework would have been to take at least one full an analysis. So here I edited my multi-analysis.bat file, and I just moved up all of the TTOF tests for the ppm test, so the extraction MZ dimension. So I did 3 ppm, 5 ppm, 20 ppm, 40 ppm, and 100 ppm. And so that, and then you would just, once you'd edited that and saved it, you would just go back here and just run multi-analysis.bat again. So that should be pretty easy. People should be able, you could do that today if you want. And before we dig into looking at exactly what that looks like, I wanted to go back to where we finished up yesterday. So we had, yesterday in the afternoon, we finished up with this TTOF DIA open SWATH. We were looking at the open SWATH data. And I think we were learning some things about the data which are gonna inform when we actually look at the LFQ bench statistics. I think we'll see some things that it's better if we understand a little bit more about what was going on in that data. So if you still have a Skyline open, go back one to the open SWATH without the assay library where we'd actually extracted the data. So this is the painful one that we didn't get the settings right on the first time. And if we open that up, then here's some of the data, and we could see that we kind of did a quick check. Yeah, okay, E. coli, you know, we get this, we see it upregulated in the A's and downregulated in the B's, and yeast, generally we see them lower in the A's and higher in the B's, and this is all what we expect. And then humans should be fairly, well, fairly consistent, right? All right, and then, so I wanted to go back to the IRTs and remember that we saw this sort of this effect in the IRTs. Like, if this is supposed to be a straight line across, what do we sort of learn about the A's and the B's from just looking at this? Now, I'm not saying that all of the IRTs are perfectly well behaved. I wouldn't necessarily use them as global standards to normalize by, but it's worth having a look at them because some of them should at least be straight across. But what do we see instead? What are the effects that you see there? Yeah, we see more in B. And then we also, since these are 1, 3, 5, I feel like I also see an effect like this. So the earlier runs, there's more in B than A, which I think has to be a sample prep issue, right? Like I can't really imagine how the mass spectrometer actually measured it 1, 2, 3, 4, 5, 6. And so like if I switch back to not ordered by acquired time, or if I order by document, that's basically the way it was acquired. I can't really figure out anything but sample prep that would have caused what should be technical replicates to look like that, right? But at the same time, both sets, when I switch back to order by condition, both sets have a decline. So that may be signal decline on the instrument or something. So that's something that might actually go away with normalization. And unfortunately, I don't yet. We have normalized 2, and we could, yeah, we don't yet have an easy normalization way to normalize all these numbers. I'd like to have, when I go to normalize 2, I'd like to see median, because median normalization is what we've been looking at, and we've already shown that if we go to view peak areas, CV histogram, and yeah, it just comes back up the way we had it. Whoops. So this is grouped and median normalization, and if we turn off median normalization, we see that it goes further. So median normalization is clearly helping quite a bit, and that may be because of that signal decline, right? That's my guess. Anyway, so those are some interesting, useful things to know about this data set when we start doing our statistics, and a good reason and I'm discovering this data set with you. I have to say, there are data sets that I teach where I really have looked at them a lot, and I have a lot more to say about them, but I'm just looking at this with you and learning what I can learn just from looking at Skyline. And I would say that we're not even really digging in as much to just getting a sense of what's happening on the chromatogram level. We did one little thing of like, why is this DGL getting picked incorrectly? But you can't possibly look at all 100,000 chromatograms here, but you can definitely get a sense of your data more if you're actually looking at chromatogram level and looking at it. So I would recommend spending more time looking at the data, and I'm actually thinking about, just this morning was thinking about the course might better be split to where we run everything in open swath, then we look at everything in Skyline, and then we run statistics, which is more how I would recommend you do things. Because if you just follow the progression that the tutorial did, it's sort of like Skyline's this other thing you can do, and then you do exactly what I think is really dangerous, is you run your open swath on the command line and then go straight to statistics. So I think you should be spending some time understanding effects and looking at your data, looking at your CVs, even at just the basic level. Yeah, you're going to get bitten by things if you're not doing things like checking your mass errors and just looking at how the data looks. Okay, so now we have in our mind that, okay, there's this signal decline effect that we hope is probably going to get normalized away by median normalization, and we definitely see good evidence that median normalization is helping us out when we look at this histogram and switch between medians and none. So that's good. And then, and so now and then I wanted to show you a little bit more about what the command line did, right? So I went over this guy. So there's multi-analysis.bat, which is just going to loop us through a bunch of different analyses. And I'm not suggesting that you're going to want to do this on your actual experimental data sets. I'm suggesting that these are the kinds of things you want to do when you're understanding your instrument and your performance before you go do the experiments, you might want to do an analysis of it. And I've now, yesterday I said, oh, I think that actually 10 and 20 are sort of equally good in this data because of those plots, these plots that I did. You know, here's 10, here's 20. I realized I probably missed something at that level, and I'm now back to thinking that the Skyline default of 10 is the best for this data, and I'll show you why. But if I go to Skyline analysis.bat, it's really, again, broken into sections. This first part is just saving the template into a directory, running the analysis and exporting a first report, reopening the document, exporting a second report, and then running R scripts on running two different R scripts on those two different reports. And I just told you that the reports were in these .skyr files, right? So here's swath benchmark.skyr, and here's peak areas.skyr. So I want to show you those files and have you have a better understanding of what they look like, where they came from, how you would get an SKYR file. So, and yeah, you can see if I go to export report, do you guys must have MS Stats in there? Or no, I don't know, maybe you don't. Do you have an MS Stats input there? No? Because you guys didn't, so frequently when we're doing the MS Stats from Skyline, we'll have everybody go to everybody can check out the tool store, tool store. And then here you can see the tools, and there are, a fair number of them, and then there's an MS Stats here. So this is how you could, whoa, oh, there it is, okay. For a moment, we had the wrong icon. So this is the MS Stats. Actually, wow, it still says Purdue University. Anyway, they're not at Purdue University anymore. But here's the tool, and it's on version. Does it show the version here? Yeah, 3.13.2. So you could install that, and if you installed that, you would get an MS Stats report. So these tools can install reports. But you can create reports and add reports to your system. So let's go back to File, Export Report, and Edit List. And we're going to click the Import button. And now we're going to go import those two reports that we had the command line export for us. So go to DIA course, data, DIA data. And then one is in LFQbench, and that's the SWATH benchmark report.skyr. And we'll open that. And that adds the SWATH benchmark report. And then we will import, the second one also. Oh, it doesn't take us back to the same folder, so we got to navigate again. So if we go to DIA course, DIA course data, DIA data, scripts, then there's this peak areas human.skyr. So these are the two reports that we had the command line export, and then we used R to analyze. So let's click OK. We've managed our views. We've added the two new views. Now let's look at them. So if you click on this SWATH benchmark, actually, let's go back to Edit List. I mean, we could preview it, but it's more interesting to look at how it's designed. So click Edit List, and click on SWATH benchmark, and then click Edit. So here's the SWATH benchmark report. You can see it's got replicate name, file name, sample name, protein description, et cetera, and then pretty much down where we got, well, whether or not it's a decoy, and then we've got total area, total fragment area, total background, fragment background, et cetera. And then there's this annotation Q value, which is the old way we got Q values. Now there's something called detection Q value. And if you want to see where, and then all these values, all these columns come out of this tree here, and if you want to see any of them, you can just double click on the value and Skyline will show you where it got it from in the tree. You can hover over any value. Where do you hover? Oh yeah. So true if this is a decoy precursor. Do you have to select it? No. So yeah. So if you go out of here and then hover over any value, you should get a tip saying the ion mobility high energy offset. So it gives you a little bit of documentation. There's also a help icon that will pop up, a help window that gives you documentation of all these fields as well. And if you happen to be more comfortable with Japanese and Chinese, you can get a translation of that too. Okay, so that's how this is composed. That's the report. There, if we switch to filter, you can see that there are no filters applied. So this is, and we can click preview if you want to see the report as Skyline presents it. So it's going to be 74,265 rows. And that's basically, I guess, 6 times 12, 376. So there's a row for every replicate for every precursor. Yeah, and that's that one. And then if we cancel out of this one and open up the peak area, the precursor peak area is scored human, and edit that, then you can see this is much briefer report. This is something that I just created for myself, and I've written my own R scripts to analyze it. It's just got the peptide, modified sequence, precursor charge, total area fragment, and detection Q value. That's the modern Q value. And if I double click on that, it'll show me that it's part of precursor results. And then you can also see that it's got pivot by replicate name. So if I click, and then finally, there's a filter here, 2 filters actually. It's filtering to make sure detection Q value is not blank, which gets rid of all the decoys. There are no decoys in this document. And then protein name contains _human gives me only the human proteins. And so then if I click preview on that, I only get 7,517 rows. Those are the so you can see it's far less than 6 times 3,000, right? Because I'm only getting the humans, and then I actually get these peak area and Q value. So I get 2 columns repeated for every replicate. So every precursor here has a single row with all the values needed in there. So that's that thing. So those are the 2 things and we can go see how the command line exported them, and then the script has R analyze them. Okay, so yeah, so here they are specified again in these report 1 and report 2, and you can take this script and modify it and have it export your own reports. You can create your own report templates, and you can have it export 2 reports or just 1 report. If you wanted to just do 1 report, all you would have to do is get rid of that, and I probably for documentation's sake get rid of all 3 of these, and then the script would just skip this second one. But if you wanted to, you can have 2 reports, 2 R scripts, and I adapt these scripts for. I've adapted them at least 6 times now for their various projects. Okay, so let's go look at what you produced from yesterday, and we're going to stay, I guess, focused on the triple TOF data because that's what we've just been looking at. I'm not sure that the Q-exactive data would have that same effect that we saw. We can look at that later in a moment if we want. So in the TTOF directory, I now have a 6664 window PPM 10 and RT 10. Everybody have that from yesterday? So if you drill in there, you can see there's a Skyline document. That's all these TTOF DIA library files. And here are the two reports. So the command line, and you can double click that and see them in Excel now. So there's that same report that we were previewing a moment ago, and here it is in Excel, and you can see that it is similar. It's 8,500 lines long. So this is from a different template. It's not from the Open SWATH template, so it has a few more precursors than we ended up with in that Open SWATH template. All right, and then similarly we have something else similar for Open SWATH, and then I would say the most interesting place again to look is down in this plot directory where we have peak area CV's PDF, and then Open SWATH peptides and proteins. And you can open that up. I guess let's open up the peptides one. So the peptides are really all the individual precursors. And this is our 10 ppm value. And you can also open up proteins, and proteins just has fewer values. So it's more features. So we would hope that it'd be a little bit more precise because there's less chance that an outlier, so, and we see that that's a little bit true. I mean, we definitely have fewer points and they're coming closer to a center. These are a bit more of a cloud. And, you know, that we just have more measurements, more transitions, more peptides to come up with a protein value. But so what's your initial impression of this plot? What do you see? What effect do you see of interest or effects? Well, so the nice thing about LFQ Bench is if you get everything sorted out correctly, it's got little lines showing you where. So I guess, let's see. Yeah, so the colored line is where it expects the thing to be, and then the black line is where it actually is, right? So there's you see these dashed lines, and one of them is the color of the dots. That line that's the color of the dots is where the thing should be, right? So this should be a twofold change, twofold. This is directional, right? Twofold down-regulated and twofold up-regulated between A and B, or fourfold. So that's log two to the 2 is 4. So, okay, so first of all, they line up pretty nicely for yeast, right? And they line up pretty nicely for human. Although human, I guess, maybe comes down a little bit lower, not that much. But then what happens with E. coli? What? So the actual results, the expected value is more extreme than what we're seeing, right? So we're not quite seeing fourfold. I mean, we have this curvature at the end that, you know, curved lines and, you know, I don't know, but so is there any reason why our data would just produce that? Well, the one that I thought of this morning was that, okay, so there's actually also a legend in here, I think. If we go here, we can remind ourselves. sample composition. So we can remind ourselves of the sample composition. So E. coli should have more in A and less in B. And we said that with our IRTs, we saw more in B and less in A. So if that were actually a sample effect, then we actually wouldn't be super surprised to see that. I mean, it's definitely to see that. We also wouldn't be super surprised to see human shifting. Would they all shift in the same direction? I don't know for sure. But anyway, definitely I thought, oh, okay, well, the E. coli, the reason, I mean, we didn't see this effect in the paper. With the paper data, these lines came very close to where they were supposed to be. So the fact that this data has this effect, to me, I was like, okay, maybe that what we saw in the IRTs is some indication that there is actually a sample handling problem, and we reduce the effect by that. So anyway, that's one thing. Now I'm going to switch and show you sort of how I kind of like to look at things when I have these analyses to get even a better view. I showed you this. So when I have multi-replicate analysis, I'll put them into these spreadsheets. You know, I'll just pull that, and so I'm to do that. I'm just going into this import log. Everybody should have an import log, right? If you go back to your if you go back to DIA data, you should at least have one import log, right? In your DIA course data, DIA data, everybody has an import log. Because if you were able to successfully finish, you should have an import log. And then if you edit that in Notepad++, you'll get this, and then you can see Skyline first saves to some new location, reopens the file, imports the data, and you can see it importing by twos, and then eventually builds an M-profit model, and then exports its first report, reopens the document, exports a second report, and then starts running the LFQ bench. And so what I was looking at is down here, right at the beginning of LSQ bench, it says SWATH benchmark CSV peptides, and it says that it identified 13,240, and then I would look at this technical variance. So that's what those plots are built out of, just pulling out of the log. And then the PDF plots can be very interesting to look at if you actually have a bunch of different runs. And so I'm going to switch to my large box where I ran everything in less than 2 hours. Can I get there? No, I lost my connection. Okay. All right. Okay, so this is where I ran everything, and here's the total time, 1 hour and 40 minutes. And then this morning, when I got in here, I actually opened up the PDFs for all of the runs in order. So if I go back and look at my my TTOF directory here, you can see I have all of these folders, and you might not even have enough disk space to do that here. But I have all the folders with 3, 5, 10, and then a bunch of 10 ppms and different retention times, 20 ppm, 40 ppm, 100 ppm. And so I've just opened up all the different ppms at 10-minute windows. So I'm not looking at the retention times. So this is what 3 ppm looks like. And I've scrolled down. We were just looking at this top plot, and I've scrolled down one because it gives me, I like this plot that sort of shows me the dispersion of the thing. So you can see it's fairly wide. You can see that everybody's a little bit shifted at this point. And then if I go to 5 ppm, it gets a little narrower and a little bit closer to the line, although the E. coli is starting to shift below the line. And if now this is 10 ppm, which I'm going to say I think is perhaps the best, you can see I'm very close to the line. This is basically the plot we're looking at. And you can see that, I'm getting narrower data, my data. So you can see sort of the dispersion of the data in this graph up here. And then if you go one more, this is 20 ppm. So this is what is suggested in the tutorial, is use 20 ppm. But to me, already by 20 ppm, I'm getting a little bit more dispersion and a little bit dampened effect. Everything's coming toward the middle. And if I go to 40 ppm, that just becomes more extreme, and then 100 ppm, even further still. So you can see how you definitely want to, I would suggest in your own experiments to do some of these types of analyses and understand what are going to be the optimal parameters for your instrument. Once you know the optimal parameters for your instrument, you're good, but yeah, doing some analyses to understand what would be best for your instrument is a good idea. And so I'm back to thinking that basically the Skyline defaults, which I've seen actually work really well on Bruker, Thermo, and SciEx. In fact, I just did a Thermo experiment on our Q Exactive where 10 ppm, and we actually went to 20-minute retention time windows, but it wasn't necessary. So 10 and 10 is a really good default for most modern instruments that I have looked at. And it really does, you can watch the CVs change as, so you can run these runs and watch the CVs change and convince yourself, because I got this completely new data set and I was like, well, I don't know, is 10 and 10 really going to be the best? And it was. All right. So, and then also on this machine, I was just going to show you quickly that, in every one of these directories also, after this processing, I actually have a Skyline document, right? So if I want to dig in more, I can double click on this Skyline document. Hope this works. No, it says, oh, that'll probably work, okay. Oh. So I have to upgrade here. That'll take a second, but it should go pretty quickly. But yeah, you can double click on these files and look at them. And if I mentioned AutoQC, we run something on all of our instruments that's uploading files to Panorama, and then you get those longitudinal plots that I showed the first day. But similarly, it's just running the Skyline command line, and it leaves the Skyline file around so that you can you can look at that Skyline file. A lot of people in our lab, when they're in the lab, they're not looking at Panorama. They're looking at Skyline documents sitting on the instrument PCs. and they feel like that's a quicker way to get a sense of what's going on. So here we are. This is our 3 ppm. We can see that maybe Skyline at this point is not doing such a great job at picking the IRTs either. When we get down to this 3 ppm, and if we do view mass errors histogram, we can see that nothing extends more than 2. So we have a mean of 0.4 and a standard deviation of 1.1. So we have this very compressed mass error histogram, but we're not really allowing anything to go past, and this is kind of high for a distribution. Yeah. So we can see that's happening, and then if we compare that to, if we go and we can open as many of these as we want, we go to TTOF, and then our 1010 is here, and open that. So even when you're even with Skyline, even when you're processing things at the command line, you can be left with a Skyline document that you can look at. Yes.
Whenever I see the histogram of the mass errors, I was wondering, so max content corrects for this mass error, right? Or tries to at least, or yeah, does that to get the sub ppm accuracy. Is this also possible for Skyline?
It's not something that Skyline does. And what?
The mean is always not centered on 0, right? So you could shift this at least, or I don't know, work with that.
Yep, definitely. And I mean, it's something that I thought about, and I actually had a parameter in the command line that would do that when we ran into one of these problems, but not something that we've done yet. So let's see. Yeah, so if we go to view mass errors, so that's a more true histogram out to 10 ppm, and so now we can really see that we were compressing things quite a bit if that true mean is at 2 with a 2.8 standard deviation. All right, well, any other questions? Okay. Well, I don't really have a lot more prepared to, I would definitely be looking at this data a little bit more. And I don't really I haven't looked at it enough myself. I've shown you some of the things that I've started to see. Haven't looked at it enough myself to have a whole lot more to say. So, but I think hopefully you go home with some decent tools with Skyline for visualization, running at the command line, doing parameter analysis, and all that. All right. Good. Well, you got 15 minutes or 20 minutes till the lectures start. Who's first? Tina. Okay. Well, so quick break. I don't know whether Betty set up the coffee yet.